Welcome everyone to Acreon tutorial series, quarter car wheel, H infinity control from road disturbance to robust ride. We've covered so far the dynamics and the equilibrium model with the perturbed coordinates, the state space and open loop analysis. Again, similar analysis as the cart pole with respect to the controllability and observability Gramian and the open loop pole plots and things like that. Then stepping into the static weighting of the H infinity state feedback, where we synthesize an H infinity controller for robust disturbance rejection. Note that there's no reference tracking. It's essentially just disturbing or rejecting the disturbance of the road input to the plant. And then additionally, we synthesized a H infinity observer, the dual part of the problem, and then packaged that into a dynamic compensator. With the H infinity observer, we looked at the noise channels that were impacting the suspension and the body rate. And so now we have a static compensator. We have a full dynamic compensator with respect to the statically weighted H infinity feedback, where it basically just pushes down on the objective criteria across the entire frequency spectrum. So it ignores any kind of different kind of bandwidth constraints that we would like to impose. So that's where we're starting to now get into frequency shaped H infinity performance, where we're identifying individual, basically first order lead lag weighting functions, or like compensators rather, that basically will shape the performance of our Q that we developed. That was the performance criteria that was operated on by WQ. The static weighting criteria, that is now going to be a function of frequency. And so we're going to have to augment the plant to incorporate the new filter states, and then we're going to have to resynthesize the state feedback per the H infinity criteria with this augmented plant, and then we'll combine that back in with the H infinity observer design. So we'll still use the same output feedback from that was synthesized before, so we can kind of get more of an apples to apples comparison on the Bodhi plots and the physical step responses and whatnot, which I'll plot in part 6, which will then be the third part, which is the mixed sensitivity comparison. So let's jump into the frequency shaped H infinity control. All right, so that did not jump to the right part. Huh, what? That was a weird link. So that link's obviously not so good. Okay, cool. So here we go. So in the frequency shaped H infinity performance, and so this is the measured output compensator. Again, same thing, dynamic compensator with that output from the observer. So before, as for mentioned, we had the K and L that were synthesized by static performance weights for the ride comfort, suspension travel, road holding, and the actuator effort. So now we want to essentially, instead of having the static weight WQ, we want to have it as as a function of S, or in the frequency domain that weights them, and basically on a shape for lead lag compensator shape, which I'm going to dive into in a moment. But first, before doing that, so instead of just blindly starting to weight the function or weight that performance criteria, let's actually analyze the passive and the static H infinity frequency responses. We can plot them with the Bodhi here. So this would be the transfer function from the road disturbance to Qi. Qi, again, is that Q vector. And then I'll just go up to it again for here. So the body acceleration, suspension travel, the tire deflection, and then the control input. So we're trying to now shape, sorry, little jumpy here. We're shaping this WQ, or we want this to be essentially first order lead lag compensator for shaping the performance criteria. And so let's go back down here. Okay. So, right. So now we're essentially doing a pole zero placement now that will then shape the performance criteria of this transfer function from R to the Qi. So we're shaping that WQ, and this is just a standard, again, standard transfer function here. I believe I put it above, but these are the closed loop C, B with the road input A, and then D is the feed through. And so I'm going to form these from before with the passive suspension and then the static H infinity control synthesis that was computed above. And so these are some function helpers, right? So this is the channel frequency response. So taking in the closed loop plant, the frequency sweep. This is just back solving for the omega. So we are taking the omega in, so we're getting the frequency response by back solving this inverted part here. And then the peak and the band. So this is basically getting the absolute frequency response value and the band and the frequency itself from the peak index. So we have the magnitude and the frequency of which the magnitude peak is at, and we're looking at that at a specific bandwidth constraint, so the minimum to the maximum of this omega, which will be important where we want to perhaps allow for low pass frequencies or suppress low pass or suppress gain at low frequencies and then emit higher frequency responses. So we basically are shaping it in this lead lag kind of mindset here. And so this is just putting together the A, the C, and the D for this analysis. We have the, let's see here, so performance labels. I did that above. So this is just now we're getting the passive response, the static response for the channel frequency response with the respective A, B, C, D. Again, this is the passive, this is the static H infinity, and then this is the frequency grid that was allocated above. And then here's our responses that we're just collecting in a dictionary. And then we have the magnitudes of the static and the passive. Note here, so for the control side, this is really just so it's not hacky, but it's like basically for the control input, obviously the passive, there is no control authority. So we want to just suppress that out so the plot doesn't look weird on the Bodhi plot. And then we have log log and semi log x plots here that we're doing for the Bodhi. Again, similar thing for the phase. That's just in line with the magnitude here. Let's see. And yeah, this is just more plotting utility here. Okay. And then I'm collecting the peak the peak magnitude and the bands that, so here essentially what we want to design or shape is that the body acceleration and the suspension travel we want to push down on between 0 to 20, so the lower frequency bands, and then emit, we don't care about it in the higher part, so that's our trade-off. So but likewise the actuator is going to be opposite, so we're going to allow the actuator to have gain to help with the suspension and help minimize that body acceleration, but we want to penalize it in the high frequency band because we don't want to excessively use the actuator at very high frequencies. We want to suppress that. It looks like I already plotted it, so apologies about that. So that's like kind of the intuition here, and then this is plot or just printing off the peaks for the body acceleration, the suspension travel, and the effort. So the wheel hop peak. So here we go. So here's the magnitude on the left, and here's the phase on the right. And then I'll jump into this a little bit more. Or I guess I could just talk through it, I suppose now. So so we can see here that the passive for the body accelerations, both are kind of mirroring each other. We have a resonance frequency around like the 10 radians per second if we scroll all the way down here. And that's where that's correlating with this peak here at 10 radians per second. Now, here is about like 30 something, and that's past our peak in bandwidth that we just said here for 20. So the peak that we're identifying here is 10. And so the H infinity controller is the static weight is suppressing that or pushing down. So we're getting more smooth ride through this peak here, and then it basically peaks out here like the passive and then rolls off. And then we can essentially see a lead effect here with the passive body acceleration, whereas the static H infinity is lagging that response, and then we kind of trade off towards the higher end of the frequency spectrum. So when we start shaping it, we'll start to basically have more tuning knobs here to shape what the magnitude is, which is more important. And then the phase, though, gives us the indication of whether it's leading or lagging. Um, the interesting thing here is that because if so above, I think the order of magnitude of the penalty on the body acceleration was 10 to 100, perhaps, for the static weighting. So really, we're allowing much more suspension travel to be emitted or to be allowed in the lower frequency band here. Again, we're not shaping anything, so this is just penalized across the frequency spectrum. Whereas the passive, basically, the gain is increased till that peak resonance around 10 to 30, and then it rolls off. So that is an interesting artifact that we'll see later in the actual step responses as well, where we're allowing for more suspension travel. So this is just something to note that, okay, if we have physical limitation here, then we might need to augment it with the constraint control on the outside or penalize this term even harder. Um, and then this is kind of a sneak preview to the mix sensitivity. We're going to get a completely different response here too, and how it's shaping its closed loop. And so again, similar phase artifact here. And so the tire deflection is mirroring the body acceleration, um, which is again interesting. And so again, we're statically penalizing it, and that's actually for this dynamic portion what I'm going to be doing as well, because I keep jumping ahead and I apologize, but essentially what's going to go on is we're going to dynamically shape the body acceleration, the suspension travel, and this actuator force. And then the tire deflection will just be static because at the moment, R is just treated as an observer quantity right now. So, well, I should say it's a disturbance input. We are not necessarily explicitly estimating R, nor are we getting a preview of like a LiDAR scan to gain what that step is in front of us that we could then have more predictive control around it. So that's just statically weighted for the shaping. But the actuator here is interesting because we get essentially this kind of like notch, which is again shaped around that. So after 10, around that 30-ish mark where that second peak here is, we're getting more gain, and then it rolls off. And then you can see it here, the phase basically. Again, mirroring a little bit of what we're seeing on the body acceleration, suspension travel, and the tire deflection. And so here, this is essentially these values are going to be used for the first order weight design. So we're going to want essentially for the body acceleration, the suspension travel, place frequency cutoffs, or basically design the lead lag such that we want to roll off before this. So basically we're going to be placing the frequencies. I'm kind of skipping ahead here, but so the omega cutoff here will be around 10, less than 10, and then less than 60. But that's where the actuator effort here, right? We want to basically kind of capture control authority at that 30 radians per second approximately, but then cut off, we want it to roll off where we don't want to have control gain later on. So starting high, ending low. And now, so I'm kind of talking about it at like kind of a high level. Now let's dive back into what's actually going on with the filter design and the math. So the first order weight design here is following that CISO, kind of like a gain parameter shelving, sort of. There's no time delay, obviously. We're trying to get this into a nice linear state space form ultimately. So the shape here is a function of frequency. And so we're going to have essentially the low and high frequency gains here. So the WI0, WI infinity. And so we can see that the zero frequency omega z is going to be basically a ratio of the low frequency to the high frequency gain, which is nice. So we're working with the same omega c, that cutoff frequency, which is indicating the transition between the pole zero locations. And so here's some intuition on just the lead lag design with the gains. So essentially, so we have this design and we have the low and high frequencies here. We could just visually see that plugging in zero and infinity. So the lead action is when the frequency of the zero is less than the pole. So the zero is acting first, producing positive phase lead through that transition band. And that's kind of what I was mentioning here. So you can see kind of the passive is leaving the static H infinity on this frequency response. Um, and so the lag is then opposite. So the cutoff of the zero is greater than the pole. So the pole is acting first, the producing a phase lag. And so that's attenuating through that transition band, which is essentially what we're going to be trying to model for attenuating noise at higher frequencies or allowing lower frequency responses to be controlled better, right? So, or at least the closed loop tracking response. That's kind of more of the mixed sensitivity side. But so the asymptotic shelf gains determine where the frequency range is. So if the low frequency is greater than the higher frequency, we're placing more emphasis on the low frequency performance. That way, it's going to be higher. So we're trying to reduce low frequency gain. And then likewise, opposite. So if the gain of the high frequency performance is high, we're encouraging attenuation in that higher frequency band. Okay. So basically, they're just opposites of one another. So the pole zero determined, I think I just talked about that. So then here we're having the nice uniform, just the one omega c, that omega cutoff frequency, because we could define the zero and the poles as the zero is going to be a ratio of g naught and or g zero and g infinity, and then the pole on the bottom. So we can see that minus wc is the pole, or omega c is the pole, and then that minus g zero over g infinity, omega c is the zero. And so we got that nice smooth transition pole zero region, which is going to be plotted below here. And yeah, so I was just talking about this. So so we're using these values as indicators down here for the dynamic weighting of the channels of the suspension, control effort, and looks like I might have forgot it, but the body acceleration. I don't know why I didn't put that there. Whatever. Oh wait, no, here it is. Yeah, so we're saying, all right, right. So the body accelerations and the suspension travel, we're wanting to penalize that at lower frequencies, right? We don't want to have a lot of oscillations that people can feel. That's not ideal or pleasant. And then likewise, we don't want to have increased gain of the suspension at lower frequencies either. That's not ideal as well. So we want to penalize that at lower frequencies. And then opposite, the controller, the actuators penalize more at higher frequencies because we want more of that bandwidth, the control authority helping those two performance criteria here for the body acceleration and suspension at lower frequency. And we don't really want it jerking around at higher frequency, wasting energy. So, and then, yeah, that was just kind of a little tidbit on the LiDAR scan if we had that as a preview. And so this is similar, not obviously same as the channel frequency response, but this is the lead lag response now with that model WI of S here. And so this is just a little function utility doing that math. And then these are the weights here for the low frequency to the high frequency, G naught to G infinity. And then the Q index is just aligned with how Q is set up initially. And then omega C is our basically cutoff or transition frequency for the pole and the zero design. So here we can see we're weighting the lower frequency much higher than the high, about 10x, again, 10x here for the suspension travel, but then this is weighted higher than the suspension travel. And then the actuator authority is less and it's opposite. So we're allowing more band on the low end, and then we're penalizing the higher. And then likewise, our cutoff is higher on the frequency spectrum as well. And so we have the lead lag response here from the dynamic channels above. This is just setting up the plot. A similar thing here with the log and the semi-log X. And then I have a vertical for the omega C cutoff, so we can see that where it's rolling off. So here's the first order dynamics of the weights, the weighting channels. So we can see the cutoff for the suspension travel is ahead of the cutoff for the body acceleration. And then the actuator effort is later on that frequency spectrum. And we can see these roll offs, right? So higher to lower weights for the comfort in the body. Comfort and the body acceleration, and then the suspension travel. But the body is much higher weighted, whereas the control or actuator effort has the kind of inverse, right? So we're allowing more actuation, lower frequencies, penalizing it at higher. And then we can see essentially here we have sort of opposite phases, right? So the actuator would, I guess, it's not, I don't want to speak too much to this, but essentially we've already covered a little bit about the lead and the lag action here and what that means and where the transitions are. So this is just correlating with the weighting here, which is really going to be important for how we get that and invert it to the time domain with the Laplace, which will be, I think, in this section. So this next part, I think, is honestly we're a little bit it's fine. It's a little bit trickier, it kind of took me a couple of times to get through and make sure that it was looking correct. So we have the our first order weighting filter here as a compensator, and so the performance weight then is the Z WI of S, WI of S, QI of S. And again, that's following the similar thing as before with the WQQ going to the performance channel, right? So that's the same outline. It's just a function of S now. And so we want it, so we have the transfer function ahead, right, from the Q to the performance channel. And we want to essentially unpack, we want to make basically revert from transfer function to a state space design. And so what we need to do is introduce an inverse Laplace transfer down here. But first we need to basically break out the numerator. So there's just a little bit of algebra here to get the dynamic weighting filter posed in a form such that we can basically isolate when we introduce a state, which will be this XWI of S. So for each of the dynamic performance states, so this is the body, acceleration, the suspension, and the control. So we have this newer state here that has some memory, and then it's a function of QI of S, right? And then these are the cutoffs. So we have the pole zero design. And so we're introducing this new state to cover this artifact from the WI of S. And we have a feed through or direct component too, and the higher frequency or gain here, G infinity of I. And so now we want to move from the S to the time via this inverse Laplace transform. And so essentially, again, a little bit more algebra, just make it a little nicer to get the S's and the omegas out, broken out in a nice way. So the Laplace transform of x dot wi of t would be S x wi of S minus the initial condition here. The initial condition is 0 for the performance state. And so basically mapping these out essentially one to one, we get the x dot wi here, we get the omega ci xwi there from that state, and then we have the wci qi here. Okay, and then just rearranging that, those are our state dynamics for the weighting channel in the time domain. And then likewise here, so for the output, we still have this feed through, this direct term. We have a state now, so we can model the ZWI of S, WI of S, QI of S. And so we have the state here on that difference from the low to the high gain, and then plus the direct feed through term on that QI of S. So then we do the inverse Laplace transform, and then we have this. So that's our output equation. And so now we have this basically like filter block or filter bank called down here. for each of the three states, and we can obviously pack them in together to make a state space form. And so we're going to augment our original dynamics and output with this new filter state. So it's kind of like it's almost like an onion in some ways. Is kind of what I like to think about it. So we have the quarter car realization here, the Q CQZ plus DQV. I'm just going to jump up above because when I was reading through it again, I didn't think it was very apparent just chucking that out. So this was in part three, I believe. If I can get to it. Is it up more? Okay, here. So I actually rearranged this part to make it a little clearer. Before I was kind of being a little cavalier with the terminology. So we have the Q here and the ZP of the performance with the static weighting WQ of Q here. And so this is enumerating now, breaking out the matrices to be a little bit more pedantic. So the CQ and the DQ, those are mapping the plant variables to the unweighted physical channel Q, so the Q here. And then the WQ right here is static weighting, and then the one below that we're looking at is the function of the frequency, right? And so now we have the CP/DP, which those are the realizations for the weighting performance output ZP. And so if you break it out, so we have the Q as an output CQZ plus DQV, and V is the disturbance with the U. And so ZP is then a function of WQQ from above, and then we introduce the Q, which is this, onto the WQ. So then we have this commutative operator here from CQ, WQ to CP. So that's where our CP and DP look like now. So I wanted to just break that out to be a little bit more pedantic on the static side. So now jumping to the dynamic side, it's a little more digestible. Um, Not there, here, here. Okay, so that's our Q, that's our BV from BW and BU. So our new state here is augmented. So we have the original state vector there, and then we have the body acceleration, suspension, and the control state dynamic state weights here, filter states rather. And then so this is the part where we have our filter dynamics from above, right? So it's a function of the X, W, and Q, but Q can be basically input. We can substitute the Q into here. And so we got that similar BW CQZ plus BW DQV. And then that V is the road disturbance in U. And then Z is obviously our original state vector. So Q is now substituted from the regular input side. So now we can really break this in, or realize the state space with the dynamic weighting operator and interconnecting it correctly now. So it is a little bit of a mouthful and it's a lot. And note that this isn't even, so this is just preparing the entire state space for the H affinity synthesis. So here the augmented A, B, C, and D are now functions of this augmented filter state and the original plant, right? So we have the A, B, V, DWCQ, and then DWDQ, which is over here. DWCQ, sorry, that was over here. So that was the performance here. So our performance outputs have been changed a little bit. The original state above, and then we have the augmented state filter state weights here. And that is going to be, we can see AW and then BWCQ and then BWDQ there, right? So the inputs and then the state there. All right. I know it's a lot. That part is a little tricky to step through. But now we have our augmented plant here, and that's what essentially this function is doing, from end to end plus end filters. And then we're just taking the dynamic channels that were created above and then plug and play in terms of getting the right positions on the augmented A, B, C, and D and placed correctly to map the right linear operators in place. And then, as forementioned, the static tire weight is static, it's not dynamic. So we're placing that in the correct position that Q is defined. Um, and so here is our dynamic weighting augmented plant, again with the static tire weight. So that's static tire deflection based off of the road disturbance. And then we're going to reuse the same exact weight from above for the tire deflection. And so here is our full dynamic augmented plant. So it's 7 by 7 for the state. And then you can see obviously, so we have 7 state variables. The inputs are the same. But then we have more uh, of these internal filter states, right? Which is the +3 from 4 to +3, 7. So cool. Yeah, that's the 4 there. So we have the dynamic weighted augmented state now. So similarly as before, we're going to do the exact kind of thing here with going from barred to the physical real and inverted back and forth, right? So scaling them. So that's non-dimensionalizing and scaling the plant such that we can make the optimization on it's this is actually maybe a little bit less than order one, but similar concept on order one to make the solver a little bit better. It was actually much trickier for the mix synthesis. I had to change the time reference around, but that'll be in the last part, so I'll talk through that later. Um, let's see. So this is this, yeah. So similarity transform, and then right. So we're pushing input onto be augmented, and then that new, I guess, state is inverted, right? Pull back on that, and then we get the be augmented barred here. So for the, and then we time reference scale the same way as before for the H infinity state feedback, and then scaling C and D in a similar way. These are the scale values from before. Filter state scale values or plucking out from the performance scale values from the dynamic weighting channels. There's the linear algebra to do the scaling. I'll just run it again. So here we go. These are our scaling. It's a little smaller. And I could probably actually use the other time reference scale too from the mixed sensitivity, and that's going to increase these values so it doesn't get too close to 0. Anyways, this is working fine. Um, so the dynamically weighted H infinity state feedback synthesis. So now we're essentially the control synthesis here. We're going to get a K that's going to be broken apart. Essentially, we're going to have a K that's operating a similar way before on the perturbed coordinates that we actually have. And then we're going to have a K that's actually operating on our filter states, the W. Not the W as the disturbance, but the XW introduced above. And so, yeah, so the gain's operating both physical and the filtered states. So the W is, so that's where it's reacting on the frequency dependent memory on the weighting filters. When we had it in the S domain and then transformed it into the time domain and then packed that into our state space, right? So that's the intuition there behind these new, that what that new controller K is going to actually do to help shape. It's an internal, right? It's an internal K that's operating on its memory here with the frequency XW weighting filters. And so we have the SOG defined above, SU, yep. So basically pushing it, pulling it back, whatever, to the physical and the barred space. And so the closed loop, A and CL here, again, pretty similar form here from what I was doing before. This is just to ensure that the transfer function from the road disturbance to the performance output per the H infinity norm is less than the gamma K from the augmented controller is strictly less than. So this is upper bounding that H infinity norm metric. And that's our H infinity certificate that we want to see post the solve to ensure that it is indeed a good, it's satisfying this performance criteria that we want for robust control. And so here's just some setup. I don't know why I have that here. I think that was playing around with something before. Anyways, dimension, and then I did bump up the tolerances just a smidge here with the dual feasibility and duality gap. It's on in 1e minus 4. I think before nominally it's 1e minus 5. So it's slacked by 10x, but it still is completely satisfied with the controller. That when we do the H infinity norm sweep as a function of frequency, it is less than the gamma k that's returned by the solver, so that's okay. And then here's the scaled plant in this new augmented form, dynamic. And this is breaking, so I'm getting the K back from the H infinity control synthesis, and this is estimating the H infinity norm similarly as before. And then this is just ensuring that it is less than the peak. Let's see, closed loop. And here's the poles, right? So getting the poles for the H infinity closed loop solver result, and then this is just printing off the boilerplate again for the H infinity dynamic result, and we're getting the peak, the frequency. So that'll be checking to ensure that we can see where the peak is of the function of frequency. I think it's going to be, yeah, it's in units of tau here, so it'll be still in the non-dimensionalized scaled units, but in the compensator form, we'll see it in the physical real side of things. This is just checking that it's bounded, and then here's the pole plot of the H infinity closed loop poles, and then the dynamic H infinity closed loop poles, so just for comparison. All right, cool. So we have optimal iterated 12 iterations. So then the normalized, so R to the performance output per the H infinity norm is bounded by the gamma. Gamma is 0.0019, that's 0.0017, so we're good. And then here are the closed loop poles, right? So we're going to have more on the dynamic weighted augmented feedback, and then we can see the static weight here. So, and it's pretty, solid pole placement in terms of this symmetric log scale here, minus 10 to the 0 to minus 1, minus 10 here. So, good pole placement in terms of stability criterion being met. And also we were meeting the H infinity norm metric. I think this is the last bit here. Not quite. All right, we're getting close. So now we're pushing this into the dynamic compensator. So we have the augmented K that was introduced above. So the original K that's operating on the states, the physical states, and then we have it broken out with the filter weight states that's in the augmented form. So our optimal control law is a function of these two. We have Z hat now, right? So we're introducing that observer estimated estimation from Z in the output of Y. So this is the same form above with the output observer dynamics, and then we have the filter state dynamics as well. This is just some substitution of variables for the U to get it into here. Right? Yeah. BWW. Sorry, let me just go up really quick. I want to make sure I didn't write anything incorrectly. Did I miss it? There's BW for the BV. Here's BWQ, Q subs. Yeah. Okay. Jeez. Sorry. A little bit of a mind fart there. A little too far. Okay. So, okay, cool. All right. So we have that from above. We just have a Z hat now. And then, so the compensator realization here. So we want Y to U, right? So we have the measured output and we're operating on that to produce a U. The XZ state is now going to be a concatenation of the Z hat, Z estimate, and the filter state XW. So we're essentially going to have the real state, the estimated state, and the filtered states. So it's obviously starting to get much more unwieldy. But trying to make sure it's all clean, at least on this markdown and this map derivation, so the code blocks make a little bit more sense and the results make more sense. So here we're saying AK, BK, CK, DK as the compensator here for the dynamically weighted state feedback with the observer synthesized from above. XC is this new state that we're introducing that has the augmented XW. And obviously that's not being estimated at all. That's just internal to the state feedback portion of the compensator. This is essentially plug and play from above. You can refer back to it. I'm just going to keep marching down though. And it's posed in a similar way, right? So we have A, B, C, D, and this again in this mapping of Y to U is the mapping that we want. So we have this transfer function here, Y to U, and again, similar form as before, just with the compensator. And so this is what we're going to analyze for the H infinity norm metric in the non-dimensionalized, non-scaled physical units below. And we'll see how then the road disturbance enters the plant and the noise also entering the measured output, how that's affecting this compensator. And so we have the compensator above derived, and then for the plant and the compensator realization, that's where we're plugging them both in with the plant again. So we have this plant dynamics z dot az plus buu bwr, same form as above. Remember the output y is cyz plus n is that Gaussian noise or just white noise, sensor noise that we've introduced on the suspension and the body acceleration channels. Note that we've introduced that XE dot above, right? So our compensator dynamics is this XE dot AK, XE plus BK CYZ plus BKN. And so we can see, so the BKCY is part of the closed loop dynamics here. The BKN is external noise input, which would be here. And then the BK as the Leuenberger observer gain and zero that we introduced above on the observer side of the coin. So the noise is entering the observer, but that directly reaches the filter states and the control input through the compensator dynamics. So in this new plant plus compensator form, we have the state vector here, which is the original Z. We have XZ, which is Z hat, and XW, the filter state. And we have inputs R and N. So R, the road disturbance, and N, the noise, right? So that's what we are analyzing here. So that's our input, that's our closed loop CL. Same thing here for the output. So the physical performance output is Q, and we have so that's augmented to be CQ, DQ, CK operating on XCL, and then for the R, for R, or wait, no, sorry. So the CQR operating on R, takes us to Q. And so that's our feed through here. And so this full state realization now is used with the K augmented above, that was defined above for the states, or for our original controller gain operating on the original states or the perturbed coordinates. And then we have the controller synthesized as part of the augmentation operating on the frequency components of the internal state. Cool. And so the physical plot step response Bodhi achieved norm checks. Wait, I think this is stale because I moved those actually in part 6. So that's not in this portion. I'll change that. All right, so this is forming that dynamic observer based closed loop system that I just walked through there. It was a little bit more brief, but it follows the exact same form as the cart pull and the other dynamic compensator above with the static weights. This is just dynamic weights, so it's a little bit more. We just have this new XE. So, like I said, it's kind of like this onion. There's just more. We're just packing more into the state space essentially for the dynamic compensator because it's kind of it's almost recursive in nature what's going on, but it's sane in the sense that we're getting, we're satisfying H infinity norm metrics. We're satisfying the performance criteria that we're going for. Everything is linear. We're getting nice pole placements here. So, everything is sane so far. Um, so here we have the dynamic observer-based closed loop that we're realizing here, the compensator and the closed loop. And so here are the poles of the output feedback, so dynamic plant plus the poles. And so we will plot them. So it's stable, plant plus compensator is stable. That's exactly what we're going for the H infinity control. Um, and let's go to the dynamic compensator check here. So as again, the certificates are good for the actual synthesized objects. So from the L above or the K, those we can check directly with the frequency response to ensure that it's upper bounded by that gamma K that's returned by the objective function, or the objective value rather. When we're forming the compensator here, we don't have that certificate, but we still can get the peak of what that Y to U gain is over the frequency sweep. And this is in physical realized coordinates. And then I'm also plotting the poles here of the dynamic weighting. So anyways, but we could see that, this is our compensator peak here from Y to U at zero point 0.1 radians per second. So in the physical part. So here's the the standalone compensator with the blue arrow, blue X rather, and then the plant plus compensator in this orange dot. Yeah, so, and then again above, these are the poles of the static weight feedback and the dynamic augmented feedback closed loop. Okay, we're just kind of building out the, the state space really, and we've introduced more states, and we have still the dynamic compensator with the original H infinity observer. So it's just getting to be a little bit larger and a little bit more complicated, but we are stable and we're satisfying the criteria that we wanted to define the weighting performance for. And this is the part where originally I had the Bodhi plots and physical steps here, but because we have one more part with the mixed sensitivity, I put that at the end. And so I'm going to look at that in the next part, and comparing all three, right? So we'll have actually four. We'll have the passive spring mass damper system. We'll have the statically weighted static output feedback for the H infinity robust disturbance rejection. And then we have the dynamically weighted per the loop shaping that we introduced. Both. It's not loop shaping on H infinity, but it's the weighted channel shaping. And then we have mixed sensitivity, where if we look at the dynamics as a closed loop system, we can break it out in sensitivity, complementary sensitivity, and the control effort as well, with that KS being the sensitivity transfer function. So a lot of stuff going on, but that last part is going to package it all up and I think tie the knot on this tutorial series. Thank you for watching. I appreciate it. Yeah, and I hope to see you in the next one.